This section will discuss continuity. So I'm going to give you the definition first and a few examples, and then we're going to actually do a few together. So first of all, a function is continuous if these three things happen. First of all, f of c is defined. The second thing, the limit at a point c exists. And the third thing is that those two things are equal. By the way, if you recall from previous sections, in order to show that the limit at that point exists, it must also be true that the left-hand limit and the right-hand limit are equal. So if I ask you to show that something is continuous, you need to show that to prove that all of these three things happen. For the second one, make sure that you also show that the left and right hand limits are equal. So this involves quite a few steps. So I'll give you some examples that are not continuous, and then we're just going to go ahead and we're going to work out some problems. Okay, so for the following functions, these are not continuous. So for number one, that one is not continuous because actually in that case, f of c is not defined. For number two, this one, f of c is defined. It actually, there is a point there. However, the limit does not exist. So for number three, 1 and 3, we do have a limit that exists, which is great. Number 3, actually, so number 1 and 2 are satisfied. We do have a point for f of c, that's right here. We do actually have a limit that exists. The problem with that one is that our limit and our value are not equal. So for that one, number 3 is not satisfied. And actually, for this last one I put down below, this should be number 4, by the way. So for this one, none of those things satisfy, none of them are satisfied. So this one is definitely not continuous. At point C, it's not defined. There's no set thing. We have an asymptote there. The limit does not exist. And of course, since 1 and 2 aren't satisfied, then we can't have 3 either. So before we work out a problem on our own, I want to go over just one more thing on this slide here. Numbers 1 and 3 are what we call a removable discontinuity. And we call it removable because it can be fixed. So what I mean by that is, like, for number 1, for example, we actually are able to add a point in there that would make this continuous. For number 3, if we were to take that point on number 3 that has an arrow on it and just move it down, that would fix the graph and make it continuous. So for number 2, this is what we call a jump discontinuity. And you might be able to guess that we call it a jump discontinuity because as the graph is going along, it jumps from one point to another at C. And then another one you might be able to guess the reason for the name for is called an infinite discontinuity. And by the way, even if both were going to positive infinity or both were going to negative infinity, it still would be an infinite discontinuity. That happens when we have an asymptote, a vertical asymptote. So for these questions, I am asking you at which x values is the graph not continuous. I actually said is f not continuous, but I called one g and one h. You can just say at which x values is the function not continuous. And if the discontinuity is removable, tell how you can make it continuous. So there's a few strategies when you're looking at problems and you're trying to determine continuity. I'm going to write them on the side. So there's three strategies we're going to use when we're determining if something is continuous. First one, always look at the domain. Secondly, you're going to see if something cancels out. If it does, you might have a removable discontinuity. And then the third one is if you have piecewise functions, substitute in actually this should say your constraint values. I am going to give you a piecewise in just a second. It just wouldn't fit on this page right now. So we'll do one of those, we'll do two of those actually in just a moment. So for number one, you hopefully will notice that the domain of this is that x is not equal to 0. Actually, if you know what that graph looks like, you might realize that there's a vertical asymptote there. If you forgot what the graph looks like, that's fine. I'll just kind of draw it like this. It's going to look like that. So even if you don't remember what it looks like, though, it's fine because you should hopefully remember that in order to find vertical asymptotes, you have to look at where the denominator is 0. So that's going to be our value x equals 0. And this one is an infinite discontinuity. For number two, we know based on our domain that it's not continuous at x equals -2. However, you might notice that this graph actually has something that can cancel out. You are going to find that the x plus 2's can cancel out. So this, if you were to take the limit, it would be equivalent to taking the limit at x minus 2. So what we can do, this is a removable discontinuity. So we know that if we were to take the limit as x approaches -2, that place where it's not continuous, of our g of x, that would actually be equal to -4. I found that out by substituting in -2, by the way, into this equation right there. So actually, to make it continuous, you need to make it so that g of -2 is equal to -4. I'm going to show you the other way you might see this written sometimes. So to make this one continuous, what you can also do is you can write it as a piecewise function. And the piecewise function would look like this. So it would be that we have this function true except when x equals -2. And then we, when x was equal to -2, we would have our value of y or g be -4. So you can write that in either way. You probably will see it written in both ways. Okay, so for the last one, the graph of cosine actually, that doesn't have any domain restrictions. So the domain of a cosine function is all real numbers. So this one is continuous. You can say at all x, or you can say for all real numbers. Anything like that is fine. So we have two more graphs that we're going to check their continuity. And first thing for both of these, you're going to look at your domain. So for number 4, that value, my domain for -2x plus 3 and x squared are all real numbers, which is good. The only issue that we're going to have is x equals 1. We are not sure if it's continuous at that value. So if you notice number 3, I said to substitute in constraint values. By constraint values, I mean the value right here, the x equals 1. So what we're going to do is we are going to check each part of that piecewise function if they are equal. If our y values are equal, meaning when we plug in the 1, that means that the function is continuous. If they are not equal, that means the function has a jump discontinuity. For the first part of the function, if I substitute in 1, I end up getting 1. For the second part, the bottom part of the x squared, if I substitute in 1, I get 1 again. So this function is continuous. Now, I think it's a good idea to draw a sketch of this also so that you can see. You aren't required to, but it's not going to hurt you to do that. So I'm going to do this really, really quickly. I'm going to draw like my husband calls it a 10-second graph. So you can just quickly graph it in like 10 seconds. So we know that the graph of x squared is a parabola. However, when x is greater than or equal to 1, it's just kind of like the top part of the parabola. This is not drawn to scale, by the way. It's not quite perfect. So that's the second part of it. The first part of it, when x is less than 1, the graph of that is negative 2x plus 3. That has a y-intercept at 3. And then I would go down to right 1, and that would look like that. So you can see if you graph, it's also continuous. You do not need to graph it every time. By the way, this should be a line, the blue part. But if you graph it, that probably will help you to visualize it. If you're super visual like I am, having a graph is really helpful. Okay, so then for number 5, you can also draw a graph for this one if you want. This one's a little bit more complicated to draw the graph. It might take you more than 10 seconds. So if you want, you can actually get by just checking those 2 equations when x is equal to 2. So we want to know, is it continuous at x equals 2? So then let's check out negative 2x. If we plug in 2, we get that equals negative 4. The next part, the x squared minus 4x plus 1. If we substitute in 2 for that one, we get 4 minus 8 plus 1. We're pretty close. Unfortunately, pretty close is not what we want. It is not continuous. It ends up being negative 3. And since these are not equal, that means our graph is not continuous, our function is not continuous at x equals 2. You're welcome to try to draw a picture of it. For negative 2x, we know that is a line that has an intercept at the origin. It looks kind of like that. So then we know that this also, we just found that when x equals 2, my y is negative 4. That's what we discovered right here. For the second part of that graph, I already found that when x is 2, y is negative 3. I don't exactly know what it looks like. I know that it's a parabola. I know that it's a parabola that goes up. So it probably goes something like this. That one, like I said, just drawing it based on what I would guess it is. Don't draw something like this on the AP test. Or if you do, just cross it out, because it's not, they will take off points if you draw anything that's not right. And actually you can see, I didn't even draw this line correctly, but I'm hoping you kind of get the idea of what it looks like. You're welcome to try to draw it on your own, but basically I want you to know that it's a jump discontinuity. That's what happens when you have a piecewise function and the 2 parts of the piecewise function are not equal to each other. So our last example in the continuity section is that we are going to find the values of a and b so that this function below is continuous for all values of x. So you do not need to draw a picture, but I'm going to draw you something so you can kind of see what's happening. So basically what we have for this piecewise function, we know that when x is less than or equal to negative 1, the y value, or f of x, is equal to 2. We know that when x is greater than or equal to 3, the y value is negative 2. But what they're asking us to figure out is what happens in between here. We can see it's a line. When I drew it, the x and y intercept were at 1. We can't be sure that that's true. Maybe it is, maybe it isn't. But we need to use algebra to figure out what our slope and y-intercept of that middle part are. You can see that it's a linear function, by the way, because it has an x and not an x squared, which is nice because those are a little easier to work with than something that has like a squared or a cubed. So let's go ahead and work out this problem. So what we want in order for this problem to be, or this function to be continuous, we want that when x equals -1, we want these two things to be equal. So we want to have 2 equal to ax plus b. And actually, we know at that point that x would be equal to -1, so we're going to write it like this. The other thing that we want is we want our function equal to our ax plus b equal to -2 when x equals 3. And actually, once again, I can substitute in 3 for x. My recommendation is if you need a second to pause the video and just think about that, go for it. Okay, so if you think about in the last section, by the way, I'll just kind of clarify it. In order for things to be continuous, they had to, the piecewise functions had to be equal. The y values that you got when you plug things in had to be equal at that x point. So let's go ahead and solve this out. Actually, please solve it out on your own. You just need to use algebra. So we're going back to stuff that you probably did in Algebra 1, Algebra 2. We have, I just solved this first one for b. I'm going to substitute that into the other equation I have. I have 2 equations, 2 variables. And we end up getting this right here. So hopefully when you solve this out, you get a equals -1. And then the last thing that you do is you find b. I'm going to substitute it back into this equation I had right here. And I end up getting that b is equal to 1. And actually, just a side note, if you look back at the line that I drew up there, this is the line of y equals -x plus 1. So you can see that our graph matches the values that we got for our answer here. So you don't need to graph it every time, but sometimes it'll help and it'll let you verify that you actually did the problem right.